So in the previous video, we talked about floating point representation, specifically the IEEE half precision, and we ventured into the IEEE single precision. And this video will do a couple of examples with the IEEE floating point single precision. So actually, I can continue to use this figure since I already have the fields written here. So let's do an example. Let's say that I have the following number and I want to convert it from floating point single precision to decimal. So the number is 0, 1, 0, 0, 0, 0, 1, 0, 1. Then the manteja is 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So what is that number in decimal? So the first thing I look at is the sign. The sign bit here is 0, which means the number is positive. And then I calculate the exponent. The exponent in this case is 133. But we say that the exponent is stored in excess 127. So, which means that we have to subtract 127 from this value. So the exponent actually is 133 minus 127. Or let me rather, I should say, like E is 133, and then the exponent for the 2 that I'm going to use in a minute is actually 133 minus 127, which is 6. Then I write the hidden one because that number is stored, is normalized before it was stored in memory. So this becomes 1. This is my hidden one. And I bring down the manteja. So this is 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, times 2 to the power of 6. The 6 I got just a second ago. So this this becomes 1, 1, 2, 3, 4, 5, 6.1, 0, 0, 1, 0, 0, 0, da da da, 0, 0, 0, 0, 0. Which is equivalent to 65 point, and then this is 5, 6, 2, 5, right? This is basically 64 plus 1, and then this is 2 to the negative 1 plus 2 to the negative 3, which is 5, 6, 2, 5, and that is my value. Now let's do another example, but in this case, we're in this example, we're going to go from decimal to IEEE single precision. Assume that I would like to convert the following value, 547.25 from base 10 to the IEEE single precision. So I'm just going to write IEEE single precision. So what do? The first thing, like I said, it's the same thing that we did in half precision first. Convert to binary. 547 is 0. I'm sorry. Actually, it's 1. 1, 0, 0, 0. 1, 0, 0, 0. 1, 1. And then 0.25 is a quarter, so it's the second digit to the right of the radix, so 0, 1. Then I'm going to normalize the number, so I have to move this decimal point or the radix to the left until I have only one non-zero value to the left of it. So I have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So this is 1.00010001101 times 2 to the power of 9. Now I need to calculate the exponent. Or the exponent. Right? So E is equal to 9 plus 127, because I'm going to store this value in excess 127. So this is equal to 136. And then 136 base 10 is equal to 10001000 in binary. And then the remaining bits, like I said, become my manteja. So these bits are going to be my M. So maybe I can write this as another step. M is 00010001101. Now I can put it all together. Oh, and remember, we don't have to actually store this, right? We don't have to store it. So, the sign bit is 0 because the number is positive, so the S bit is 0, the number is positive, and then I have 8 places for the exponent, 1, 2, 3, 4, 5, 6, 7, 8 for the exponent. This is my exponent, 1, 0, 0, 0, 1, 0, 0, 0. And then the remaining bits are for the manteja. So I have 23 bits, sorry, for the manteja, right? So 1, okay, and then I bring down this value here, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, and then the remaining bits are 0. Okay, and that's it. This is my M. So this is essentially how we convert from a number that is in decimal, non-integer decimal value, into IEEE single precision. There are certain considerations. So one might ask, how do we store much larger number or much small or a very small fraction in single precision? The answer is there is a finite number of numbers that we can actually represent with 32 bits, and that's why we have a IEEE double precision, and we have the quadruple precision. So it allows us to store larger numbers, or it allows us to store like very, very small numbers in memory. So nonetheless, I'll just mention, like I said, I'm not going to go into details with the double and quadruple precision for the IEEE format, but I can tell you for the double precision, you actually have 64 bits instead of 32 for the single precision, and you have 1 bit for the sign, same thing, and then you have 11 bits for the exponent. So you have 11 bits for the exponent versus 8 that we saw earlier, and then the remaining bits will be for the manteja. And obviously, because you have more bits for the exponent will be in excess 1023 versus 127. And as you can see, the exponent can be really large, right? So it could actually go up to 1023. So it allows you to store larger numbers. It could be more to represent like smaller numbers and so on. The quadruple precision, basically they double the amount of numbers or the amount of bits. So now instead of 64 bits, you have 128 bits. Okay, and then for the exponent you have 14 bits, and so on. So like I said, we're not going to go too much into details here, just something that, to mention. It might be useful, we might find useful. There is a little bit, some maybe more information on the single precision. How do I represent 0? Like, how would you, if you have 0, there is no leading one. How are you going to normalize? Like, if you have a 0 decimal, base 10, how are you going to write it in binary? So in binary, it's going to be a bunch of zeros, right? But then how are you going to normalize it? Well, the convention is actually, if you have a lot of zeros, well, not a lot of zeros, if all the fields are 0, that is a 0 in single precision. So if, forget about the sign for a second, but if the exponent are all zeros, and then the integer are all zeros, then this will represent a 0 in memory. If you have a 0 here for the sign, then you have the positive 0. So this will be a positive 0 here. And if that sign bit is 1, then you have a negative 0 in this case. Another consideration, or another special case, is if you have a 0 or a 1, and then the exponent bits are all 1s, the integer are 0, that represent infinity and negative infinity. And then finally, if you have a 0 or a 1 here, and you have 5 1s for the exponents, and anything beside a 0 here, let's just say here, anything but 0, then this is not a number. And that's it. Now you know how to convert numbers from decimal to IEEE single precision, and from IEEE single precision to decimal. You know how to normalize a number, and you get to know a little bit about the double precision and quadruple precision IEEE formats. Thank you for watching.